Today we will be studying ionic equilibrium. Before that, we need to know some concepts which we will be coinciding with electrochemistry. First, let us know what is electrolyte. Electrolyte is a solvent. Electrolyte is a solvent which forms ions and which helps to conduct electricity when electricity is transferred through it. It could be liquid or it could be a solution where ions are involved. And sometimes we also consider solid as electrolytes, but those are basically the metals which have the electrons flowing through them. So that's basically what is electrolyte. Now, coming back to ionic equilibrium, the key concept of ionic equilibrium, the first term which we will be explaining is the ionic product of water. Ionic product of water. Now, water itself is a very weak electrolyte. Why? Because water is a polar substance, polar compound. It forms it undergoes partial ionization. It does not dissociate completely, rather it dissociates partially. Now, if we want to write the equilibrium reaction of the water, we can see it undergoes a reversible reaction. So that means it sort of have a balanced, it sort of have a like two-way direction reaction where it partially ionizes to form H plus and OH minus ions. That means if at a certain level the concentration of hydroxide and hydrogen ion becomes more or increases, the equilibrium will shift to the leftward, producing less amount of H plus and OH minus in order to balance the equation. Now, that is the main or crucial part which makes water a weak electrolyte. Now, the part here, the concentration of the product, if we describe that in terms of its concentration, so we would be saying the product of the concentration of H plus and OH minus is known as the ionic product of water. At the same time, this should be at a specific temperature or a particular temperature. Now, let's describe it in terms of its equation. Recalling our previous knowledge on Kc, equilibrium constant, if we have a reaction, we tend to write the reaction in terms of its product and its reactant. So on the product side, we have the concentration of H plus and OH minus. So we are going to simply multiply the concentration of H plus and OH minus of the two ions divided by the product or the left-hand side compound. So H2O, the concentration of water. Now, if we simply move this H2O to the left-hand side of the equation and multiply it with Kc, we would get Kc times water, which would simply give us, or we will be left out with H plus and OH minus, the concentration of H plus and OH minus, their product. Now, this left-hand side, we can simply write it as Kw. This Kw represents the ionic product of water, and as I have mentioned, the definition itself specifies it is the product of the concentration of H plus and OH minus. Let me repeat again. It is the product of the concentration of H plus and OH minus. That's why Kw is the ionic product of water, which we can write the equation as Kw equals to H plus and OH minus. Now they have certain specific characteristics. The first key characteristic is the reaction is itself an endothermic reaction. I'll be coming back to it in a bit after a while. So it is an endothermic reaction. The second point to be noted is the value for the ionic product of water is 1 into 10 to the power negative 14 mole square m to the power 6. Now, as I've mentioned while giving the definition, it must be at a specific temperature. In this case, this value is at 25 degrees centigrade. So that means since I am stating a temperature here, with temperature, this value is going to be changed. So we can sort of say the Kw, it changes or it depends on the temperature. Now, if we increase the temperature, the Kw will increase. If we decrease the temperature, the Kw value will decrease. So we can say it sort of has a proportional relation. Since the reaction is endothermic, if we write the reaction again, which was Kw equals H plus and OH minus, with the, since this is an endothermic reaction, we know in endothermic reaction, as temperature, like before saying what will happen if we change the temperature, the forward reaction is the endothermic process. That's why we name it, like we name the reaction type in terms of its forward direction. So the forward reaction or the forward direction reaction is the endo and backward is the exo. That means if temperature is increased, the equilibrium moves to the forward direction, and if temperature is decreased, the equilibrium moves to the backward direction. Because in forward direction, the temperature decreases or the temperature is tend to decrease. In dynamic equilibrium, like this is a state, this reaction itself, when we were having a reversible reaction sign, that means it obviously must have a dynamic equilibrium state. What happens in a dynamic equilibrium state? It tends to regain its equilibrium position if any change is brought to it. So let's say our reaction is A plus B, reversible sign, C plus D is the product. So if any change has been brought, let's say the reaction occurs fine at 200 degrees centigrade. So if I make the temperature increase to 250 degrees centigrade, the reaction or the system will try to change the state in such a way that the temperature decreases and it is reduced to get back to 200 degrees centigrade where it is its optimum temperature. On the other hand, if we would have decreased the temperature to, let's say, 150 degrees centigrade, the system would have taken initiatives so that the temperature rises and regain its equilibrium position. That means this 200 degrees centigrade was its equilibrium position. We know in reversible or in dynamic equilibrium situation, in dynamic equilibrium reactions, there are other factors also included where pressure is another factor, then concentration is another factor, but we are like currently we are sort of dealing with just the temperature. Coming back to the Kw part, since the reaction is endothermic, if we increase the temperature, that means we have increased the temperature. Let's say the value of like the equilibrium value or the dynamic equilibrium value of temperature was some T value. We have increased it to T max. That means it has increased. But the optimum solution was at T. The optimum temperature was T. It would try to reduce the temperature, but how would it do? We know endothermic is such a process where in forward direction, the temperature is decreased. While exothermic reaction, if the reaction moves towards the exothermic reaction, the temperature increases. In endothermic, the temperature is decreased. If I try to explain it in much simpler term, then it would be like for endo, the system absorbs the heat energy from the surrounding, while in exo, the system releases heat energy to the surrounding. So in endo, absorbs energy. In exo, it releases energy. Now let's think of an example. If you think of a mint chocolate, what does happen? In a mint chocolate, if we give it in our mouth, our like mouth tends to like become like the temperature falls. The it tends to cool down our like the how do I explain? Like the temperature of our mouth like it decreases. That means it is actually absorbing. Like it doesn't have any sort of like agent which is like actually decreasing the temperature. Rather, it is like absorbing the temperature from my mouth towards the system, or into the system. However, if we if we take a situation where, let's say, we ignite fire, what will happen? The fire will tend to like release energy to the surrounding. That's why the surrounding temperature will tend to increase. That was what happens when like we are beside, the let's say kitchen. So that means if we increase the temperature, we have to move towards to the direction where the temperature will be decreased. And we know in the direction of endothermic, the temperature decreases because in endothermic system, the system absorbs energy. So it will help to decrease the temperature, reduce the temperature. That's why the forward reaction, which is the endothermic process, if we increase the temperature, the reaction will move to the forward direction. However, if we would have decreased the temperature, what would happen? The system would try to increase the temperature. Now we know the backward direction is the exothermic reaction. And in exothermic reaction, what it tries to do, it tends to like release energy to the surrounding. So if the temperature is decreased, how can we like regain the higher temperature? Obviously, we don't have any other source of heat. We have to provide energy, or we have to release energy. So that's what the system does. From itself, from its inner side, it releases the energy to the surrounding from the system. That's why the equilibrium moves to the backward direction to increase the temperature to regain the equilibrium position. Now, let me erase this up. If we rewrite the equation, we'll see H plus OH minus. Try to have a look. Like if the temperature is increased, the equilibrium move to the forward direction because endothermic. What will happen? Moving to the forward direction will produce more and more H plus and OH minus because the reaction is moving to the forward direction. So that means the concentration of H plus and OH minus would have increased. What does that mean? That means more H plus and OH minus ions are formed. That means more concentration of H plus and OH minus. As a result, the product value will be higher. If the product value will be higher, that means the Kw value will be higher, isn't it? Kw is actually what? Basically, Kw is Kc times H2O. Or if we like just simply write the actual equation, like the dissociation reaction, which is like, I'm sorry, like I made a mistake here, which was Kw doesn't represent. We are not supposed to write the Kw with a reversible sign. Like Kw is basically this, but where we will be writing the equilibrium sign over here, H2O equilibrium sign, H plus plus OH minus, like writing the equation actually. So while writing the equation, these are the like dissolved substances, and this is the simple compound, so which is not soluble. That is just simple liquid H2O or just simple H2O or covalent substance. Now, if we move to the forward direction, obviously more H plus and OH minus is formed. That means H2O is getting dissolved more. So value of H2, like the concentration of H2 is decreasing and concentration of H plus and OH minus is increasing. Since temperature is increased, equilibrium is moving to the forward direction. As a result, the concentration of H plus and OH minus increases, hence the Kw value should have increased. Why? Because if Kwe is H plus and OH minus, if higher value of higher two values, let's say H plus is 2, for example, H plus is 2 and OH minus is 2, multiplying them, we will get 4. But if let's say the concentration of H plus increases to let's say 4, and also H minus increases to 4, what would we have get? We would have get 4 times 4, which is 16. Means the value of Kw is now much more higher. Similarly, the reverse happens if the temperature is decreased. If temperature is decreased, the equilibrium move to the backward direction to reduce the temperature. Sorry, to increase the temperature. In order, like in the direction of like the backward direction, which is actually the exothermic reaction. So moving to the backward direction, what does that do? It actually decreases the concentration of H plus and OH minus. As a result, more H2O is produced, so a concentration of water increases, but the concentration of these ions decreases. Concentration of water increases, but concentration of these ions decreases. If that happens, that means what? If let's say this was initially 2 into 2, which was 4, now the concentration of the ions decreases to let's say 1 and 1. Multiplying them, we get 1. That means Kw value decreases. If these are like just random numbers I do, for example, those are not the real numbers, but just for the simplicity of the situation. So that's what it is. That means this is the value of the Kw at the room temperature, 25 degrees centigrade. If the temperature is higher, that means the value should be greater than 10 to the power negative 4 or 1 into 10 to the power negative 4. If the temperature is lower, the value should be lower. Now, speaking about the ionic equilibrium, the one thing we can describe here is we can take a look of the actual reaction, like which happens here. So let's say the two water molecules, like the ionization part, so H2O and H2O liquid, they tend to react together, forming the H2O plus ion, which is the hydroxonium ion, hydroxonium ion. At the same time, there will be a hydroxide ion. These are aqueous state. This is the same as like this hydroxonium ion is similar to single H plus ion. So we can write this equation in another way, which is H2O plus H2O, like the main thing which actually happens, which is H2O liquid plus H plus aqueous plus OH minus. So if we tend to like try to compare these two equations, what we can see is like this H plus was written actually like trying to break it down to H plus and H2O. This is actually the actual form of hydroxonium ion. Hydroxonium ion contains this part actually. There's a water molecule and a H plus ion. So this water is sort of it is acting as a like spectator. So let's say from the left side we take a water, and from the right side we take any of the water. Like if we consider these two reaction, what do we see? This is completely unchanged. So we can say this water is the spectator, and we know spectator is what which remains unchanged in like both the part, like in while the reaction is initiated and while the reaction ends. So the actual reaction which happens is H2O liquid, H plus aqueous plus OH minus aqueous. So this is actually the main reaction. So recalling or trying to remember this is good, but like trying to like but remembering this it's fine. Anyone would work, but I would say like try to know the hydrochlorium ion, like what is it, like knowing about it, it's better to know. But yeah, writing this is completely fine. So that's basically the ionic equilibrium part, the ionic product of water part of the ionic equilibrium. Now let's ascend. Let's proceed. pH. So far, we have in all levels in areas, like we have heard about a lot about pH. But what actually is pH? pH is actually negative logarithmic function, or the negative logarithm of the hydrogen ion, which is called the pH. So we can write the equation simply, which is pH equals to negative log base 10 of the concentration of hydrogen ion. That is basically what pH is. And there's another term which we didn't heard much, but still that exists, which is POH, which is also the negative logarithm of the hydroxide ion concentration. That means POH is basically negative logarithm of the hydroxide ion. That means now if any sort of p value, let's say any px value is said, that means that px is actually negative logarithm of that substance's concentration. So that's what actually this term means. Like we would get only these two terms. The other terms actually they don't come, but for the sake of the knowledge, I just told. Now we can do a slight calculation, which is if let's like how do the pH calculation we do? Like how do we do the pH calculation? If let's say for example, the concentration of HCl is given as 0.2 mole per dm cube. If we write the equation where HCl, like dissociation reaction, obviously all of these reactions are all like partial dissociation reaction. So if we write a reaction HCl, we will get H plus and Cl minus. So these are not complete ionization. Complete ionization would have like simply a single step reaction, like single direction, like in one direction reaction, forward direction reaction. But these are all like partial dissociation reaction, which are like reversible reactions. So if we are given the concentration of HCl, which is 0.2, that means we can molar ratio it with the product, which is 0.2. If it is 1 mole over here, if you consider, that means H plus is also 1 mole over here. As we can see, the equation is balanced. That means HCl is to H plus is 1:1. So we can say 0.2 mole of HCl would be equivalent to 0.2 mole per dm cube of H plus. If that's the case, then we have the concentration of H plus here. And if they ask us to find the value of pH, we will simply use the equation, this formula, which is negative logarithmic function of the concentration of H plus, in this case, which is 0.2. And we will get simply value, which would be, let me calculate the value, we will get 0.2. Which is basically 0.69897. That means, which is less than pH 1. And we know in the pH chart, the pH value 7 is the neutral. And if you move to the left, that's acidic. To the right, that's basic. And since it is towards the left, around like somewhere near 1, that means it's very acidic, and that means our result is giving the correct solution. And also don't worry if the result is in negative, because that would have also given us a correct answer, because negative pH value also exists. That means that's too much acidic. Okay. So that's basically the part of pH value. Now, if we are asked to find the, let's say, pH value for 0.25 mole per dm cube of CH3COOH, then what would we do? Now, say, or so we simply we could guess that we could use the same formula, like same process just we used before to find this value. But hold on a second. This CHCCOOH, this it itself does not undergo, like it is a very weak acid. So it is for sure it undergoes for a partial ionization. One thing I didn't mention here, like this equilibrium we would give, like we can give for writing the Kw value, but while calculating the pH value, we can simply just work as if the reaction is happening in the one-way reaction for calculation, just for calculation. But over here, this CH6COOH, we cannot even consider it like in a one-way reaction. This is a purely like very weak acid, which is like which undergoes partial ionization reaction, and there is a stage where which causes like, difficulty for us to calculate this pH value in the simply just plugging and like doing this following equation. But why is it so? The main reason is it doesn't actually sort of give us the correct molar ratio or the equilibrium molar ratio. If we just see the part over here on the left and on the right, we can say that over here we have 1 mole. That means over here we also have 1 mole. So the molar ratio would be 1:1. So the acid is to H plus, the molar ratio would be 1:1. But that's not the case here. In order to study it in depth, there is the term which is Ka, which is acid dissociation constant. Now, what is acid dissociation constant? It is if a substance is, let's say, is ionized and it forms its ion. If we write the Ka value, we can write in K capital A or K small a. Correct. So Ka, we would simply write H plus and A minus divided by Ha. This only happens, or we can just do the acid dissociation constant only for acids. Remember, for the pH, it's also like possible for the like for calculating pH. It's also possible for the alkaline, so like alkaline values or alkaline solution, non like neutral solution. Like every sort of values, like they have the procedure like, to follow in pH. We can calculate the value of pH like in the general term for any substance, but for acid dissociation constant, only the acids are like considered. So as I have written the equation over here, we can like still work with this, which was, so if this is the reaction, it's this is the equation. Now, see one thing, it actually dissociates how? It actually dissociates under water. Underwater, what happens if this H plus and this H2O they combine? What does they form? Hydroxonium, as we have just seen previously. H3O plus. Forming this hydroxonium ion, what causes is like this imbalance in their concentration. So if we write the Ka value, which is Ka equals to, like in simple terms, if we before writing this, we can just break this down, which is H2O plus H2O plus H plus. We can see this is the spectator. We can cancel that out. And what we will be left with is CH3 COOH and CH3 minus plus H plus. Now, if we write the acid dissociation constant value or the equation, which would be this is like the normal Kc, the normal terms we have written in Kc. So which is C, the concentration of the products concentration values of the product. Product of the concentration of the products divided by concentration of the reactant. Now, there are some assumptions we need to make. The first assumption is the hydrogen ions are produced only by the CH3COOH. Now here is the term. Why? Obviously there is a water, and we have just seen in Kw part, water itself also dissociates. That means if water itself also dissociates, there is the presence of H plus ion for the from the dissociation of water, as well as there is the presence of H plus ion from the dissociation of this acid. That means there is the presence of two types of hydrogen ion, or the source of hydrogen ion are from two different compounds. One is water, another is acid. If that's so, we are just considering in this case that this H plus is being considered only from the acid. We are not considering H2O. Why? Because we are just calculating value for pH of CH3COOH. That's why you cannot take the consideration of the water's H plus. So that's one assumption. If that's the assumption, that means there will be some error. Okay, so that's one of the assumption. The second assumption is the number of H plus, and like the simple term, like if CH3COOH is causing the formation of H plus, that means there is no H plus from water. And at equilibrium, we have to consider the concentration of CH3COOH is equal to the initial concentration of CH3COOH. Initial concentration of CH3COOH. Now, obviously, there will be some error. Why? Try to think if this does react, or if it does dissociate. Obviously, the value of CH3COOH is going to decrease. Why? Because it itself has to break down. After breaking down, it is going to form the H plus and CH3COO minus. Now, if we consider that equilibrium and initial CH3COOH are equal, then where did that used up CH3COOH went? And since we don't know actually how much CH3COOH is used up and how much is left in CH3COOH, like how much CH3COOH is remaining in the equilibrium, we actually need to consider